Hi everyone. Hope everyone is doing well. And yeah, good morning, good afternoon, and good evening to whichever part of the world you are. And welcome everyone to the session on automating supervised machine learning pipelines in Python. And today we have an awesome lineup of guests. We have Dr. Thomas Eves, who is a lead data scientist at UL Prospector, and he's also the founder of Integrated Machine Learning and AI blog, where they keep posting some awesome stuff about machine learning, AI, and other related topics. At the same time, joining in, we have Lewis, who's the data science consultant at World Bank, and also we have Tina Mary, who is a data practitioner and passionate about analytics and visualization. So today's session we will be mostly focusing on how we can automate supervised machine learning pipelines and how important they are and what role it plays in terms of automation and how it can help you in your future projects too. With that, probably I'll let Tom take over the session. Tom, it's all yours now. Thanks a lot for joining in.
Thank you, Chanyuka. Guys, hello. We're really happy to be here together. Let's just look at that title again. Automating supervised machine learning pipelines. As you can guess from your own learning and trials in life, theory is hard enough. But then when you start to implement things, it really gets challenging. So that's why we say this a little bit at a time. And we've got this disclaimer warning here. This talk may raise many questions. We hope you count that as a good thing. And this morning, I was just talking to Lewis and Tina, and we love this material, but we thought, how do we want to present it? And as we were talking how we wanted to present it, I prepared this for my systematic Saturday post on LinkedIn, and I'll just read it out loud. As I write this, I'm about to present with Lewis Owen and Tina Mary to DeFi. Our material is essentially the basics of supervised machine learning. I've encountered many great mentors in many forms throughout my life, really. One powerfully recurring principle taught by them: the greatest practitioners in any field take the time to master the basics. And the basics are the foundation of any great art in life. Masters literally practice the basics tens of thousands of times. And I'm all for the coolest tools and techniques, but they will crumble as a house with a poor foundation if not built on good basics. So really, that's the spirit of this talk. Okay, this is going to look busy right away, but I want you to think about any pipeline that we create for machine learning as being much like picking fruit. If you've ever had that experience, you know that every piece of fruit you pick is not worth eating. Some of it's been pecked at by the birds or burrowed into by the worms, or it's just gone rotten. And so we have to be careful which fruit we pick. And that's a lot about what this is like. You may feel like you just stepped into an airplane cockpit and you're looking at too many gauges that you don't know the meaning of. Some of you may be looking at this and going, finally, someone put it in a relational form. But really, it comes down to just some repeated basics over and over. We start at this highest level, and really the pipeline is about managing features, which are like our inputs, managing our labels, which are our outputs, and then exploring models that do the best job of using these features to predict these outputs. But there still needs to be human involvement, and we're going to talk about that too. One thing I want y'all to remember, though, is that our data comes almost always as a sample from a population, and we can't always know how biased that sample is and what forms it is, but it's never perfect because it's just a sample of the population. And if we could take all data of the population, our systems may not be able to handle it. So that's why it's so important to understand these principles we're going to go through and reduce it down to the essentials. And with that, I'm going to turn this section over to Tina.
Thank you so much, Tom. Okay, so this is our, we are in this slide, and in the coming slides, we will be discussing about the most important component of our pipeline model, which is the features. So with features, we basically mean the variables that you have in a data set and how we'll be going about the different dimensions of the features. Okay, so first we are going to be discussing about the missing values. Can you move to the next slide, Tom?
Yes.
Okay, so when you deal with data, it is very obvious that you will have missing data. So it needs to be, so before you move into any modeling process or any exploratory data analysis, it is very important in order to handle all those missing data. But before you go into handling of those missing data, the first and the foremost thing that you must do is understand if the missing data in your data set shows any kind of patterns. Sometimes the data can go missing at random, and that is not actually a problematic situation. But at times, it can happen that the data that is missing from your data set can show particular patterns. Let me help you understand with the help of an example. Suppose you have a data set that includes data from different retail stores of a particular company, and you see that the data from a particular retail store is continuously being missed out. So, in such situations, adequate measures have to be initially taken in order to in order to make the process of data collection in that particular retail sector a very good one, and then we need to move into the handling of missing data. That being said, a handling of missing data can be done in two ways. Either you can go for deletion or you can go for imputation. When we say deletion, deletion can be adopted in situations where the data goes missing at random. And there are mainly three methods, as you can see in the figure given there. You can delete the rows, you can do pairwise deletion, or you can delete the columns. But deletion of data is not always advised because deleting data can result in losing really valuable information. So apart from deletion, there is another method which is called imputation. Imputation basically means that you substitute the missing value with a calculated numerical value that can be found from the data set. So the imputation method can depend upon the type of problem that you are dealing with. Sometimes you can deal with time series data problems, and the time series data that you're dealing with will have a seasonality component, trend component, and depending upon the kind of data that you have there, different imputation methods can be suggested. As you can see, data without trend and without seasonality, in such kind of data, the mean, median, mode, all these values can be used as an alternative for the missing values. And likewise for the rest. And if the problem is very generic, it can either be a classification problem or it can be a regression problem. So in case of both these problems, the data can be categorical or continuous. So for if the data is continuous, it is always better in order to go with substituting the missing values with mean value, median value. But always the best practice when you're dealing with continuous data is to predict the missing values using linear regression method. And if the data is categorical, then one method that you can use is using logistic regression in order to predict the missing value. Do you have anything more to add, Tom and Lewis, to this?
Just real quick, I love this powerful concept or practice really of we're just inside the features, but if you're careful about it, you can produce missing values with modeling, but you're still just within the features. So you're treating that missing value as the output. And it's just a very powerful. And then you're using the ones in that column. The column is a feature that aren't that are there. You're using those as your labels. Then you get to use. It's kind of like if y'all are already familiar with this train and test split. The areas with the missing values are the test set, and the ones with the ones present are the train set. So you train it that way to predict those missing ones. That's a very powerful way to deal with missing data. Thanks for covering that.
Yes. Are you? Can we move to the next slide, Lewis?
Yes, Lewis.
Yes, please.
Yes. Okay. Great. So now we've dealt with missing values, and now we are going to the next dimension, which is cleaning of data. So most of the time in data projects, it is very obvious that the data that you'll be getting is very messy, and messy data can be very challenging also. So most of the time, when you're dealing with messy data, it is very important to be in your senses and to be calm and try to clean the data with so much patience. Because most of the time, people think that data scientists do very cool things like modeling and predicting all the results in the future. But the reality is that most of the time, researchers say that almost above 70% of the time, the data science process, the 70% of the data science process is mainly used in order to clean the data. And I think Tom would beg to differ with me here because he would say it would take almost 80% of the time.
Probably more than, but you're doing great.
Okay, so that being said, that is what I've tried to show through the first figure there, and you can see that almost 79% of the time that is actually spent for collecting the data sets as well as cleaning and organizing the data. And the second figure, you can see a very generic pipeline of the data cleaning process. I have to tell you, this is a very generic, it is not confined to these processes alone. You can have other steps too, but this is a very generic overview of the data cleaning process, and it has mainly three phases. The first phase is the screening of the data. So in the screening of the data, okay, now you have the data in your hand. So first, what you should see is, do you have adequate data in order to do the data modeling process or data prediction or the analysis that you're going to do? Do you have enough data? If you have enough data, then it is well and good. But if you don't have enough data, it is very important that you collect adequate amount of data. And if you have more than what you need, you just need to break it down into the most important the most important and required amount of data that you actually need. And how we'll be doing that, we'll be discussing in the later slides. And then in the screening process, you have to see if you have any outliers in your data. The outliers, usually when people talk about outliers, the first thing that they are going to do is drop the outliers. But that is actually not a best practice. The outliers in your data can tell a lot about the kind of data that you're dealing with. Okay, so the once we need to check for outliers or strange patterns. That is what happens in the screening process. And in the second phase, you diagnose. In the diagnostic phase, what you mainly do is you check for the missing values. And as we can use the previous in the previous slide, we discussed about how we'll be able to do that. And we can check for errors and missing data. And then there might be outliers, which you have identified. And there might be cases where the data that you're dealing with some of the variables might not be in standard scale. For example, if you're calculating the distance between any two places, sometimes it can be written in meters and sometimes other values can be written in kilometers. So you need to standardize all those values. And so normalizing the values we need to check whether you need to normalize all those values. That is the second phase. And in the third phase, you have identified all that needs to be done. You have identified the procedures, what and all to be done. And in the third phase, you do all that. So you correct all the missing values, you treat all the outliers, and you delete the data that is unwanted. And if you feel that the data feels good that way, then you leave it unchanged. Okay, so anything more to add here?
Louis?
No, I'm good. You've done a great job, Tina.
Okay.
Great job, Tina.
Okay, so now here we are going to deal with the encoding of text. Louis will be taking over from here. Over to you, Louis.
Thank you, Tina. Okay, so we'll move to the feature encoding part. Remember that machine learning in data science is all about numbers, but we can also encounter text formatted data, right? So can we keep using those text data? Of course, yes. However, we have to find clever ways to transform those texts as numbers. Or in other words, we have to encode those texts. When we have single words describing something, the words merely represent a category, and we can convert those categories to numbers into separate features, one feature per category. And basically, we do this by representing its category as a binary number, 0 or 1. And this method is called one-hot encoding. However, there are categories which have an ordinal characteristic too. When I said about ordinal, it's actually like the word have a level on our order information. For example, salary level categories such as low, medium, and high salary. And one-hot encoding can represent these types of characteristics. So instead of encoding the category into binary number, we can convert those categories into 1, 2, or 3 respectively. This method is called ordinal encoding. It's also common to have poorly formatted text as features, for example, customer reviews on products. And handling such things gets into natural language processing. But we will not cover this for now. For now, we just want to cover at a high level the types of features that you can encounter. Okay, so dealing with text as inputs can seem intimidating initially. Please do not let this stress you. We'll show you how to encode text features in a good ways later in our articles. Okay, so do you have anything to add, Tom and Tina?
No, that covers it. And I think the most important point you made was don't let converting words to numbers stress you out. There's always some simple, elegant way, and it's a Google search away.
Cool. Okay, let's move to the next part. It is the normalization. Actually, Tina have covered this a little before, but I will cover this again. Okay, so normalization. So you have all your features in the numerical format now. But those features have their own units or value ranges, right? Let's say you want to build a machine learning model to predict the body mass index of humans. You plan to use height, weight, hip circumference, and chest circumference. It is clear that each of those features has its own value ranges and units. Adults' normal height is ranging from 150 to 180 centimeter. Weight is ranging from around 40 to 100 kilogram. Hips and chest circumference is ranging from around 85 to 120 centimeter. So maybe you ask, why if those variables have their own units or value ranges? What is the matter? So, there are some machine learning models which are sensitive to this difference. It also will make the optimizer of our models needs more iterations to achieve the convergence. So it is important to normalize our data, so that it will become unitless and has the same ranges of value. And how to do that? The most common method used is standard scaling. Basically, what it does is to make a feature has zero mean and variance of 1. There are also other types of normalization out there. We will cover that later in our articles. Do you have anything to add, Tom and Tina?
That
Tina?
was good.
One thing I like to point out is, let's say you're just doing linear regression, which is wonderful and powerful. By scaling all of the features, now they're all on an equal playing field, and the model parameters themselves tell you which features contributing the most to the model predictions. And that's what I find most powerful about this particular point.
Thank you, Tom. Okay, let's move to the next part, reduce. Let's get this to Tina again.
Okay, thank you, Louis. So now we come to the reduction part. Okay, so there is a very common misconception that as the number of variables in the model increases, the model accuracy or the efficiency of the model also increases. So when I say efficiency, it can depend upon the type of metric that you are using to calculate it. It can be accuracy, it can be precision, or it can depend upon what is the best measure for efficiency for your model. But in general, let's say as the number of features increases in the model, it is not always true that the efficiency of the model will also increase. So sometimes if we have two variables if we have more variables, if we have variables that contribute, that does not contribute any value to the model, then it will affect the efficiency of the model. It will take a higher amount of time for training the model and related issues. So it is always important to find the only right amount of features that will contribute value to your model. So we are going to discuss about that in this slide and the coming few slides. So here we'll be seeing why we need to reduce the features. So can you go to the next slide, Tom? Great. So collinearity. This is a word that will be very familiar to most of the people listening to this talk. So let me try explaining that with the help of these graphs here. So in the first graph, you can see that the limit and age are plotted against each other. And in that scatter plot, you can't see any particular patterns. So both these variables are independent with each other, and they do not have any relationship between them. But in the second graph, you can see that limit and rating are plotted against each other, but you can see a clear positive correlation between limit and the rating. So as the limit increases, the rating is also increasing. So this is a typical case of collinearity between those two variables, limit and rating. So in order to tell a very technical definition of collinearity, I might say that collinearity is the near linear dependency between any two independent variables. See, dependency between independent variables. So why is it so bad? Why is collinearity so bad? The collinearity basically undermines the statistical significance of independent variables. They are supposed to be independent, but they are not. The change in one variable is directly affecting the other variable. So in such cases, when you have variables that are collinear in your model, it would be very difficult in order to separate out the individual effect of these variables. And the problem can be even more worse when it comes to regression problems, because when a change in one variable results in a very big change in the other variable, the regression coefficients can vary too much, and it reduces the accuracy of the estimates of the regression coefficients. So due to all these reasons, it is very important that we deal with collinearity in our data set. And I'll briefly skim through all the sources and the rest of the topics here. So one of the we are going to discuss only 2 points here. So the one source why you can have multi-collinearity in your data is because of inadequate data collection. So it is always expected that the data is collected from the whole cross-section of the population uniformly. And the sample data that you're taking for analysis has the data collected from the whole population in a very uniform manner. But sometimes it can happen that the data is collected from a very small subsection of the population where there might be some kind of population constraints applied on it. And this will directly be shown in the kind of data points that we are collecting. So this can be one of the reasons why we have collinearity in our data. And another reason can be due to the over-defined model. The over-defined model, basically what I mean through over-defined model is that when the number of variables that we have is greater than the number of observations we have at hand. These kinds of situations can actually occur in medical sample surveys when suppose we are trying to understand the effects of a particular disease in humans, and we have a lot of variables that we are considering, but the number of people who are having that disease is very less. So in such cases, we will have an over-defined model, and it can lead to collinearity. And how do we identify collinearity? It is actually one of the most simple and initial ways that we do in order to identify collinearity is using a correlation matrix. So when you're using a correlation matrix, you will be those variables that are having very high correlation values will most probably be collinear to each other. So when you plot the correlation plot of the independent variables, you can just skim through it and see which and all variables are having very high correlation values. So, but correlation metrics, identifying collinearity using the correlation metrics can be used as initial step only. Once we find that we have collinear variables in that, we need to go for the second method in order to confirm on that. And also using correlation metrics also has another disadvantage that sometimes more than two variables might be correlated with each other, and that situation is called multi-collinearity. And correlation matrices won't be a very good solution for to identify collinearity in such cases. So we go for variance inflation factor. The variance inflation factor will tell you about how the coefficients of your regression are varying in your model. But there is actually we can find the VIF values for each of our variables, and the threshold after which the collinearity becomes a problem is still a matter of argument among all the researchers. But some say we have to take 5, some say we have to take 10, but we have to understand that as the VIF values of our variables keep on increasing, our statistical model becomes less reliable. And in the last part, we have how we can deal with collinearity. That can directly connect with the sources of our collinearity. And if we have less amount of data, we should collect more data. If we have collected data from where there are some population constraints, we should avoid collecting data from a population where there are some population constraints impacted upon them. Or lastly, we can retain one of the variables that is showing collinearity and drop the other variables that is related to them. We should only keep the most significant variable, and we will be discussing on how we should do that in the later slides. Do you have anything more to add here?
Tina, you gave a great illustration recently, kind of an analogy of collinearity, like two people trying to do the same job.
Mm-hmm. Oh, okay.
You give it. You do it well.
Okay, so sometimes it can happen that, let me say that analogy that I shared with Tom. Sometimes it can happen that you're in a team and there are two people doing the same job in the same team, but that is not actually, so the output, the efficiency of the team will not be as good as if both the people are doing unique jobs to the best of their ability. So if they are doing it in that way, then it will be the output of the team will be much more effective. It will be much more efficient. So that is one way that we can use an analogy to define collinearity here. So,
excellent, very
yes,
good.
Thank you. So here we dealt with collinearity, and in the second part we have correlation. And I'll be discussing about the methods we use in order to identify correlation. Tom, next one.
Yes.
Okay, so correlation is a very generalized version of collinearity, actually. So we defined collinearity as a near linear dependency between any two independent variables. But correlation, the correlation is a near linear dependency between any two variables. It can be independent or it can be dependent. So the correlation values can range between 1 and -1. So when the correlation value is 1, we can see a perfect positive correlation between both the variables. And this mainly implies that as the value of one variable increases, it will result in a corresponding increase in the other variable. And a correlation value of -1 basically implies a very perfect negative correlation, implying an increase in the one variable will lead to a corresponding decrease in the other variable. So when we are dealing with regression problems, it is always expected and it is the best in order to have a very high correlation between the dependent as well as the independent variables. Why? Because we only need those variables in our data, in our model that will have very high predictive relativity with the target variable that we are trying to predict. So when we deal with correlation, there are mainly two methods in order to find correlation between variables. One is the Pearson's correlation coefficient, and the next one is the Spearman's rank order correlation. So both of them gives a correlation value. So what is the difference between them? Pearson's correlation coefficient is basically used when the data that you're dealing with is basically a continuous variable. And Spearman's rank order correlation is used whenever the data is ordinal. And what do you mean by ordinal data? It basically means categorical data, but within all the data, there is a clear ordering or a ranking of all the variables. So that's with correlation. And now Lewis will be taking over from here. Over to you, Lewis.
Okay. Thank you, Tina.
Yes.
Okay, so Tina already explained how we can use the direct method to measure a correlation. And besides using the direct method, we can also use the help of lasso regression. Basically, lasso is just a linear regression with an added penalty terms in its objective function. So the penalty is called L1 regularization. And what is L1? It is only a sum of the absolute value of our coefficients. So this lasso aims to not only minimizing your objective function, but also to minimize the value of your model's coefficient. Okay, we can also use our machine learning model and select the most correlated features based on our metrics. How? We can just look through each feature and try to expel it from our set of features. Then, look how is our metric response on it. If it is better, then throw that feature from our set of features and the other way around. Instead of trying to expel each feature, you can also shuffle the order of value of that particular features and look your metric response. Okay, so besides of metrics, there are two other things you have to keep in mind when selecting important features. The first one is generalization, and the second one is parsimony. You have to make sure that the selected features are generalized enough. It is also important to have a mindset that simpler is better. Simpler here means a lower number of features, and that is the meaning of parsimony. Okay, we can also use PCA or principal component analysis to reduce our features as well. But instead of truly removing the feature from our set of features, PCA generates the new set of features, where each feature is the linear combination of all of our initial set of features. That is why I call this as a soft feature reduction method. And the interesting thing is, those newly generated features can be sorted based on the variance explained. Or in a simpler words, those features can be sorted based on how well they represent our initial features. And how it can be done? It uses the eigenvectors and the eigenvalues type of math. Okay, do you have anything to add, Tom and Tina? And I believe Tom will add something to this.
Yeah,
Um,
guys, go ahead, Tina, you first.
Okay, thank you. So Lewis wonderfully explained about the metrics there, and there is one component that is called generalized there. And when we say generalized, when we model the data, we'll be dealing with one particular sample of the population. So it is always, when we are modeling a pipeline, it is always best. So we need to model it in such a way that whatever data that we feed into the pipeline model, the model will be able to give the best accurate results. So we should not try overfitting the model to fit a particular kind of data. We should always keep in mind that different kinds of samples can be provided into the model, and still the model will give a very good accuracy rate or the efficiency.
Thank you, Tina.
Oh,
Yes.
good clarification. Yeah, we just basically don't overfit, pass through the data in a reasonable way. But I have a near and dear spot in my heart for PCA because of my control system background. Love eigentype math. And there were some questions about, well, what's the difference between correlation and collinearity? It might be good to cover that briefly here and more in detail later. But when we're talking about correlation, we're talking about how strong a feature relates to a label. But you can say that two features are strongly correlated to one another. When two features are strongly correlated to one another, that is collinearity. We don't want the features to correlate strongly to each other. We want all the features that we're going to keep to relate strongly to our labels. And with PCA, you get a great powerful peek of the features into which ones are most powerful. So even the modules that are available in Python take the principal component analysis and the eigenvalues and it ranks them to the ones that have the greatest variation first. And so that way, if you're trying to decide, oh, I've got these two features that are collinear, well, which one should I keep? The one that PCA tells you has the highest eigenvalue. Lewis.
Okay, yeah. Let's move to the other part. This is the feature engineering. Please move to the next slide, Tom.
Yes, sir.
Okay, thank you. So imagine you and your three other friends are in a focus group discussion, where each of you is telling your thoughts about the discussed topic. And each of you can only keep giving your own thoughts without listening to others. But it is not a FGD if there is no discussion, right? Okay, maybe you say in the end you guys come up with a solution that is purely based on a person's thought. But during the process, the four of you should interact with each other and have a discussion. And many times, the best ideas are a hybrid idea that came from the group talks. Please go to the next slide. So keeping the same spirit with FGD, we can also let our features interact with each other. Even if it is just an addition of one feature to the other one, or a multiplication, or a polynomial combination, there's a lot we can do with our raw features to build a new one. But how to refine our new set of features? We can simply perform a feature reduction in our new set of engineered features, just like we did on the set of raw features. Sometimes we will also use the deep neural network or DNN as our model. And when we choose to use DNN as our model, we have some additional benefit. That is, we don't have to handcraft our features. Because the model already created, quote unquote, those features by itself. But it certainly comes with a cost. We need to provide an enormous amount of data and much more time to train the model. And sometimes feature reduction also helps with when we are using DNN as our model. And it's often in the industry to choose the classic machine learning model in higher priority than using the deep neural network model. Okay, do you have anything to add, Tina or Tom?
Tina?
I think that was very wonderfully explained.
One thing I like to just keep in mind for myself, a lot of times we think of only deep neural networks, and we shouldn't. A neural network can be a very simple, elegant architecture. It doesn't have to have many nodes and many layers. And so we can still explore a neural network at the same level as linear regression or logistic regression. But we can, if we do careful feature reduction and careful feature engineering, then we don't need as big of a neural network to fit the data. And it can be very powerful that way without having to have the massive data needs.
Yeah, exactly. Okay.
Okay, so we've actually finished talking through all the features at a high level. And now we're going to labels, and I'll just take over here. I just wanted to add this one little point about labels. Labels, of course, are outputs. We're using them to help us in the training process. But sometimes you can actually even engineer the label. I got tripped up on a technical interview one time because I had never seen this before, but it was done very cleverly. And I want y'all to be aware that it can be done, and it can really simplify the modeling process and make it more explainable. So it's a great thing to keep in mind, and sometimes it may even make sense to scale the labels. But again, just treat it as an exploratory option. Okay, now we're at the point where we've got a clean set of features. We've got a good set of labels, and we want to split that data into training and test sets. Well, how do we go about that? Well, first we need to randomize or shuffle the data. And we added this term shuffle because the Python machine learning libraries use this term. And again, we split that data into train and test. And our favorite way to go about this is cross-fold, k-fold cross-validation. I'm going to show an example of that here in a moment. But as we go through those folds and do a training and prediction for each of those folds, we've got to look at the metrics. And as we pointed out, generalization is super important. As Tina just really eloquently explained, we're working with current samples. And I saw some good questions on this point too. But we're going to get future samples. How do we deal with those? We've got to make sure the models that we're running do the best job of generalizing across samples. And then sometimes we just get to a point where we need to explore retraining a new model. So this gets into the importance of considering automating all these processes. But we're going to get to that slowly but surely. So we want to improve on the growing data as we can. So we change the model as needed. But I've literally seen PhD candidate students only introduce one model. And one thing we really want to stress today, regardless of what supervised learning branch you're going down, there's no free lunch. Because we've sampled from a giant population and we don't know what the quality of that sample is necessarily, we need to run through all the models and see which one does a best job on the metrics. But as you're considering those metrics, keep parsimony in mind, meaning you want the simplest model that does an adequate job. And so again, this is a motivation for automation and choosing the right model. Now, to go into a little more detail on cross-fold validation, let's look here. We just want to make sure everyone understands this perfectly clearly. Here, if we look straight down, every one of these rows is the same data set. But in the first iteration, we take this part and say it's going to be the test data, and the rest is going to be the training data. Then we store the metrics for that given model, and we choose the next test data, and then the rest of it is the training data, et cetera, et cetera. Now, it can be an art form how many folds you choose, and there's been a lot of arguments in the literature. It's a hyperparameter, seriously. I mean, not strictly speaking, because it doesn't belong to a model, but the point being there's an art picking it, and it pays to explore. I usually start out at 7 and vary between 5 and 10, but 7 to 10 usually serves me best. But this is a very powerful method. And one thing you're looking for is not the greatest accuracy in one of these folds. You're looking for the model and the hyperparameters for that model. And we haven't talked about hyperparameters just yet, but we will. We're looking for the best model choice with the best hyperparameters that generalizes very well across all these folds. Then we can have the greatest confidence that it'll do good with new incoming data. And then finally, and by the way, there's something, and it's just because of our time limits, and this is an intro to a big series of posts and presentations and training, but I glossed over hyperparameters. The models each can have knobs, basically, where we can tune those models to perform slightly differently. And I do think it's possible to automate even the choice of those as we get toward automating all this. But the main thing is to understand this whole layout, this whole map that we showed that's nonlinear in nature, although it can be linearized, is a process, a basic process you want to follow. And as you master those various sections of it, there are opportunities to automate it. But even once it's all automated, and even when you do the toughest form of automation, which is picking those hyperparameters in an automated loop, it's still going to require human oversight. You know, think of any team. You've got this great performer. That team still needs a coach. It still needs a supervisor. It still needs a manager. And just because you automate all this doesn't mean you can just let it run freely. There may be times where you realize, oh, I got to go fix something in the process. And that's why we emphasize you want to aim for automation, but you always need to overwatch the process. So now, hopefully, when you see this all together, you realize this is just a beautiful way to find beautiful fruit and throw away the rotten fruit that we don't want to eat, and making really good predictions with the pipeline. Now, again, whether you get this to automation for a given problem or not is not so important as understanding how all these relate to one another. But there is great opportunity for automating this. And again, even once you automate it, you're going to need human oversight. And guys, forgive me, Tina and Louis, anything to add and wrap up?
I think that was wonderfully said, Tom.
Yeah.
Well, that's high praise coming from you too. Thank you. So guys, we're so glad to be here. And I'm going to go back to this slide, and we're going to start entertaining questions. We're eager to take them.
Great. Perfect. Thanks a lot, Tom, Tina, and Louis, for the wonderful session. So yeah, we already have a bunch of questions which poured in on different channels. So I'll probably pick one by one. So to begin with, we have a question from Vinay Rai. Let me just pop it up on the screen as well. The question is, would building training sets be a subset of collecting data sets?
I'll try to take it.
Yeah.
I'm not actually, the more I think about the question, I'm not sure I understand it. I will speak around it a little bit and hope that it will help.
Yeah.
I consider a super valuable skill creating useful fake data. Because when I say would building training sets, well, how would you build it? The way I like to build them is from the collected data set and using cross-fold validation. I always want to use that. It's not like you have to always use it, but it's a good idea to use it. There's certain types of data where that's not as practical, of course, like in time series data. And we might even invite Ashish to answer that if people want to get into that. But the point being is I think that the answer to this question, most simply put, is yes.
Okay, great. Yeah, thanks, Tom. So going to the next question, we have it from Deepta. For ordinal encoding, do you manually define the boundaries for each index? Or
Louis,
is
can
it
you do
something
that one?
else?
Yeah, maybe I'll take this one. So actually, when we say about encoding, we have the text variable already in our data. So we already have the high, mid, or low categories, and we want to encode those texts into the number format. But maybe when you ask about like how to define the boundaries, maybe you more asking about the binning the variables. Like we have the continuous variables and we want to binning those variables. And actually it can be done based on the like, as you say, like using the percentile, or maybe it can also be done using our agreement with the business team or the stakeholders, like how to define those boundaries. Do you have anything to add, Tom and Tina?
I think that's well put, personally.
Okay,
Yes.
great.
Yeah, great. And coming to the next question, we have it from Jairam. If features are collinear in nature,
Okay,
can we
I'll take
drop the
that one.
feature?
Good.
So sometimes it can happen that yes, features can be collinear, and dropping the features can be used as one of the worst cases, because sometimes, as Tom told, PCA can be used as a metric in order to understand which feature that we have to keep. So if we have 2 or 3 variables that are collinear to each other and they give the same amount of same kind of value to the model, it is very resource inefficient in order to keep all those all those variables in your model. So in such cases, you can use PCA in order to find which variable explains the highest variance in the data, and you can just keep that particular variable in the model, and you can drop the rest.
Yeah.
I just want to ask Chen Yuki, if you could, these questions coming through, I doubt we'll be able to answer them all, but we want to collect them all. And guys, what we will do as we develop our whole post series, we will make sure we address these, if not today in our blog post and other areas. And also we're having opportunities to present this in other places and even do the whole series in some places. So we'll make sure we keep Chanyukya in the loop on that, so you guys can attend those free sessions and know about the blog post as well. So I just wanted to add that. And great answer, Tina.
Yeah.
Yeah, perfect. Definitely, Tom. We'll definitely do that. I mean, we'll collate all these questions and I'll have it share it across to you. And yeah, next is what is the appropriate VIF value we should consider for independent variables? And alongside, I'll also couple this question with another question. Given a data set where you don't have the option to collect more data or drop variables, you find that variable X and Y are correlated. Can you transform the data to
Okay.
reduce the VIF
So,
factor?
depending about the VIF factor, as I already mentioned when I was speaking about VIF factors, in different literatures they say about different thresholds for the correct like till the they in some literatures they say that the VIF value of 5 is the threshold and up until which the collinearity can be entertained. So any values that will have VIF which is greater than 5, it should not that should be treated, and that will be treated as a severe multicollinearity. But in the textbook that I'm currently studying, when I'm trying to learn about VIF, in that textbook, the author prefers a VIF value of 10. So it is still a matter of debate among the researchers itself, which value is a perfect threshold for a multicollinearity. So I am not I am going to say a perfect answer for that question. It is still debatable depending upon the kind of the amount of errors that you can manage in your model. I think you can select the VIF value depending upon that.
Okay. Maybe, yeah,
Okay.
unless Tom or Lewis wants to add something, we can probably go to the next question. Yeah.
Yeah, let's go on. This is a good line of
Yeah.
thought.
Yeah. I think the next question is, given a data set where you don't have the option to collect more data or drop variables, you find that variable X and Y are correlated. Can you transform the data to reduce VIF factor?
Transforming the data can be involved with scaling of data. Sometimes it can happen that when data are in a different scales, it can happen that multicollinearity can occur. So one of the methods in order to do that is you can try scaling the data in order to bring it to the appropriate kind of ranges, and then you can try applying the correlation or the VIF factors. And remedies to reduce VIF is similar to the measures that you will adopt in order to reduce the multicollinearity. So basically, I told about that in the last section of my slide, where you can collect the appropriate amount of data, or you can select the data set from a sample of the population where there isn't any population constraints applied on them.
Got it. And okay, we'll probably go to the next question. What if one pair of features is positively correlated and other is negatively correlated? How to deal with them?
It can be. What if I'm not actually getting the question here? It can depend upon the variables. Like variables can be correlated with each other. It can either be positively or negatively correlated. But I don't see how that is going to affect the model. So can you
I,
take this, Tom?
I'm going to just try to interpret. We'll do our best here, Anushka. It Don't get wrapped up in the sign is what I would encourage. Get wrapped up in the degree of correlation between features and keep the one that's most powerful. Just because there's a negative or a positive, that's not as big a deal as the fact that they correlate strongly. Sign change is relative.
Got it. Yeah. And okay, Tom, we have a question for you. So we have from Ivo. How can we talk about explainable AI when using PCA?
So I hope I don't make people angry. I'm still on the fence about how much I want to support explainable AI. And great question, Ivo. I don't mean to belittle your question. It's just that it's funny. People walk through their house and they flip light switches, and most people that do that are using it and don't know why all that works. But then we get to this, and we have something that is reproducible and validatable. And to me, explainable AI depends more on us as data scientists doing a great job using visualization to show why our modeling is better than what we're currently doing. In other words, we don't want to move to things that cause harm, but if we can show through visualization without the people that we're trying to encourage to use what we're showing them, they would have to become data scientists for us to really be able to explain it. So I always kind of want to understand we need to do a better job explaining what explainable AI is in the first place. If we can just show, look, here's a switch, we turn it on, this great thing happens, lights happen. If we have a model and we've got this data and we're able to visualize and prove that this model's doing a much better job than the methods we've been using, to me, that's explainable enough AI. But if someone's going to demand that, no, I need to see the model parameters of a deep neural network as clearly as I can see a linear regression, I just want to politely stand in the face of that and say, look, we chose a deep neural network because the feature engineering was so complicated and humans just can't do this as well as the machine learning can. But here is the verifiable results, and we're going to be constantly monitoring and overwatching this. If you need more explanation than that, you're going to hold back the benefit of this art from mankind. I'm sorry to preach so long on this, but I'm still a student of explainable AI. But as I try to talk with my great friend Rafe and explore this, I'm thinking I really need to get my mind. I haven't had the time to really figure out what do people really mean when they say explainable AI. And so I hope I'm not sounding like an idiot on it. But anyway, we need to test and help people understand this is beneficial over what we've been doing, and here's how we're going to monitor it. Sorry for going on so long.
Yeah, totally. I mean, totally aligned with that, Tom. Also, just to add something to what you're saying right now. So I had been working on explainable AI for a while now. So there are some, I mean, basically when you're using some black box models, right? There, I think explainable AI comes in handy to explain, especially to the business teams who have no knowledge about what's going on with the black box model. I think that's when probably using some packages like SHAP or Lime might come in handy. But I think that's totally to a different session altogether. Maybe we can have a elaborate session on that at a later stage. And we have next question on here from Lania. In a data with features with binary values and some features with real values, how do I deal with standardizing the features? Do I leave the binary features and only normalize the numeric features?
Do
you want to take it, Tom?
I can take it if you don't want to, but I was going to let you take it. Let's both answer it, Louis. You back me up and disagree with me if I'm wrong. It'll be fine. I think it's just as you put it. In other words, if we turn your question into a statement, yes, Depo, I agree with you. We do that, meaning standardize the numerical features and leave the binary features alone. That's what I would do. But then, explore too. See, well, what happens if I try something else? But I don't know what else you would try, frankly.
Yeah, I also agree with you, because when we normalizing the binary feature, it turns out it also to binary feature again, because we only have two different kind of values in there. So yeah, I will leave the binary features alone and normalize the numeric features.
Got it. Yeah. Good. So we'll go to the next question now. We have this from Satish. Who performs the automation of supervised ML pipelines? Is it a data scientist or ML engineer? And the second question is, should one have deployment experience for this automation?
I'll take it and ask Louis and Tina to back me up. I love or questions. So should it be the data scientist or the ML engineer? Yes, it should be one of them. It's a team sport, right? And so it doesn't really matter who does it, but I think it's best to do it as a team.
Yeah.
Yes.
And Yeah. Probably I'll move to the next question we have from Andrew William.
And good question, Satish. I didn't mean to make light. That was an important question, by the way.
Yeah, true. If we generate more data from existing data sets, would there be bias in our added data? Like maybe I'm assuming they're referring to data augmentation or something called as you're basically creating synthetic data from your existing data.
Thoughts, guys? I've got some. Y'all add to me if you want. So let's think about it. The data's there in an existing set, and we're going to use SMOTE or GANs or something fun to create more data from that existing data. Well, you're basically cloning your data, right? Well, if whatever data problems there were with the existing set are going to be replicated in your clones. Even with the GAN, I mean, the GAN's trying to create data that looks, indistinguishably the same from the other. So you're just reproducing more of the same problems your original data set had. Hopefully your original data set was awesome. And if you just needed more data, then those techniques are going to serve you well. If your data was crap, you're just reproducing more crap. So that's my take on it. But Louis and Tina, you have anything to add to that?
Yeah, I agree with you, Tom.
Yeah. Yes.
Yeah. And we have next question from Shritik. In case of encoding categorical features, how do we deal with categories in test data, which were previously unseen in the trained dataset?
Oh, okay. So actually for that one, we can create we can just transform those variables into the mode of our categorical variables in the trained data. That is what I will take. How do you think, Tom and Tina?
Well, when I saw this question flow through while you guys were talking, I realized, oh, you have to start all over. I mean, the foundation of this whole process is getting those features all cleaned up, the clean fruit we're going to use. And if you just add a new feature, time to start over. And that's one reason I love to, even if it's just semi-automatically automating this process, that's why I like to automate those things. Like when I'm thinking ahead of time, okay, what if I have to add a new feature? Okay, well, then that way I can, if I add a new feature, I can just run back through the process, and it's not, this disheartening deal like, oh, I got to do all that again. No, I already automated it.
Yeah. Okay. So, yeah, probably should I move to the next question, or unless
if Vignesh feels like we answered it, absolutely.
Yeah, great. And yeah, probably yeah. The next question is k-fold cross-validation required in each and every step of data while building model? Okay, I think this could have been probably
Louis,
this needs
Tina?
a little more context, or yeah, go ahead, please.
Well, I think I see what Jay is getting at.
Yeah.
A set of data while building model. Again, you don't always use cross-fold validation. For example, if you're doing something that's more time series oriented, it would be, I think it would be kind of weird to use cross-fold validation. So, everything we've said really just applies to supervised machine learning pipelines. But we have a dear friend in the audience, Ashish Patel. He's written a book on time series analysis. I would refer you to him or his book. Those would be examples that when you're just trying to understand the data, you're not going to always do cross-fold validation as you're exploring things. You're just getting things set up. Don't feel like you've got to cross-fold everything. But when you're getting near the end and you're really trying to pick the model and it's not time series, yeah, you really want to use cross-fold, I think, most of the time.
Yeah. And yeah, we'll probably go to the next question. How do we do hyperparameter tuning for large data?
Well, Very carefully. But
Yeah.
I will say one thing I learned the hard way is don't try to do something akin to 1, 2, 3, 4, 5. You want to do something more like 1, 5, 10, 20, 50, 100. And then if you're thinking about trying to automate hyperparameters, I kind of am a fan of what is a really crude star search. Basically, you might start with 1, 5, 10, and that's a pattern you can replicate at different orders of magnitude. And so if you hit the boundary on one of those as a best hyperparameter, then say, okay, now I'm going to explore 5, 10, and 50. And if 10 ends up being the best one, you can stop or you can narrow in. But hyperparameters, not always, but typically aren't so sensitive that you have to, go, oh, 10 was the best one in that search. Now let me check 11 and 12. No, just do orders of magnitude, do log scale searches. And then when you land in the middle of where you currently are, you can maybe narrow down a little bit. But to me, that's the wisest way to try to automate that stuff.
Yeah, got it. And yeah, probably.
Can I add something, Chanyuk? I just want to add something, guys.
Yeah, go ahead, please.
Those of you that are listening, a lot of this, we know you guys are smart, but we also know this is new to you. So don't judge yourself if you're not understanding everything we're saying. What's important is to get like one of those practice data sets from scikit-learn and play with that. And keep this presentation handy while you're going through those. And as you start to play with one of those practice data sets, here's what's going to happen. Oh, that's what Tina meant. Oh, that's what Lewis meant. Oh, that's what Tom meant. This is going to become much more clear with some practice on just some toy data sets. And don't ever let anyone talk you out of Kaggle not being real world or those data sets not being real world. They're actually pretty close to real world. Yeah, you didn't have to go collect the data, but that's great practice to understand this pipeline much better. I hope that helped.
Yeah, totally. I think this backing is definitely required. And I think often people churn off getting intimidated, but I think they need to follow it with passion and persistence over time, and they will be there. And yeah, totally aligned on the data set spread as well.
When we go to that opening statement we had that I'll post on LinkedIn later today, it's like saying, wait, you want to be a master of this? Well, you did it on some practice data, right? And that's one way is you become a master in this pipeline.
Yeah, totally. And we will probably I think we are slightly running over time, but probably I'll pick last 2-3 questions maybe. So we have a question from Nasreen. She says, what is the difference between list-wise row deletion and pairwise row deletion? This is slightly out of context, but probably, yeah.
Okay, so when we deal with data, sometimes a particular value of a data can be missing. So we can just move forward and just delete the particular, just that particular row of the data that is missing. That is mainly that is the main thing behind row-wise deletion. And in pairwise deletion, I am not actually very sure about what that means. So do you know about that, Tom?
I think he might have meant column deletion. When you delete a whole column, you've made this decision, I don't have enough data for that feature. The column is typically oriented as a feature, or that's the way we normally orient the data. And so we're just making a decision, I don't have enough data for that column, and I can't use the rest of the features to predict the missing values well enough, so I'm just going to delete it. I think that might be what Nasreen was getting at.
Yeah, probably. Yeah, probably we will also ask, take her follow-up question.
Good.
And yeah, so there is another question, how to fill missing values for logistic and logistic regression and linear regression maybe by throwing some light on missing values would help, I believe. So yeah.
Tom had wonderfully explained that in between when he was explaining about the PCA, and we can consider the missing value as the target variable that we are going to predict, and we can use the other features that are available in the data set as the independent variables and try to predict that particular missing value as the as the target variable. That is one way that you can use linear regression as, and the same applies for logistic regression too. You can logistic regression. The difference between both these linear and logistic regression is that linear regression is used in regression problems, whereas logistic regression can be used when the data that you're dealing with is categorical.
Yeah.
Excellent.
And we have another question from Gaurav. It would be great if you could elaborate the importance of PCA in the supervised learning pipeline. Does it become very important when we have large data?
I always want to defer to Tina and Lewis, but if they want me to do it, I certainly will.
Please go ahead, Tom.
Okay,
Yes.
I love PCA just because it's
Yeah.
so akin to my control system and generalized multi-realm physics modeling background. But so again, let's just say we've got some collinear features. We're trying now. We realize, okay, feature A and feature B are collinear. We want to know which one to keep. We keep the one who, when we do the principal component analysis, which gives us the eigenvalues, we typically want to pick the one that got the largest eigenvalue because it has it's showing the greatest variance. And but does it become very important when we have large data? I would say the larger the data, the more important it can be. Again, these are all stops along a path that we visit as we're doing the modeling pipeline. Does it always pay to visit PCA? Yeah. Will you always make a decision, even automated such from PCA? Not necessarily. But
Yeah.
good to explore.
Yeah. And yeah, actually, like, PCA is one technique that I learned. That was the first variable reduction technique that I learned myself during my master's. But yeah, do you think, I mean, like, still the industry uses it vividly, or are there any advanced techniques that came in place at the moment? What do you think of it, Tom, generally?
Here's the way I like to look at everything we've talked about today. I have a shop that's out this way on my property, and it's too messy right now, but I love having tools. Some tools I use, like my electric drill as a electric screwdriver. I use that a lot. I have a scroll saw. It's really good at cutting fine angles and curves. I've used it once since I bought it many years ago. You want to treat all these things as great tools to know about, but this is cool, sexy stuff. We don't necessarily always do this. We do a lot of data cleansing, data visualization. I'm getting to do what I think is pretty sexy work now, but super challenging. But a lot of it is I got to invent, and I can't invent it if I don't know the basics really well. It's because I know the basic concepts that I can conceive of the more advanced things that no one's built before.
Yeah, totally, I agree. Yeah, I think learning and getting to know about them definitely helps, and it also lays as a good foundation for knowing some of the advanced techniques out there, which are right now applied in the industry. Moving on, like, probably we'll pick one last question. Okay, probably, like, they are asking for presentation, which we will anyway share. In these times of drag and drop modeling systems, how much focus should be rendered on building models and then on analytical outputs of model?
I'll lead off, and then I want Lewis and Tina to fill in if they want. This is kind of how do I compare this? It's like robots, guys. These kind of systems aren't going to take data scientists away. We must be masters of the concepts. We must be masters of the philosophies. You're still building models. I mean, really, well, let's put this in a nutshell. When we use the scikit-learn library and we use the models in there, it already is pretty much drag and drop. It's just that we're typing, but we don't have to go build ordinary least squares solving or gradient descent from scratch. It's great to know how to do that stuff from scratch, but you still have to understand what went wrong. Oh, I forgot to deal with the collinearity. And that's just one example. It's just that, let me read that in these times, how much focus should we it just depends on where you're at in serving your business. You want to be a great data scientist? Go talk to your business counterparts. Find out what their needs are. Apply your skills in the best small incremental ways to start bringing the value of data into their decision-making processes. That's what you really need to care about. I'm kind of redirecting the question that way, but there may come a point where, yes, you still need to, even if you're using Azure or some other drag and drop toolkit, you're still going to need to understand the principles to do a good job on that. But more importantly, you just want to focus on making friends with your business counterparts and making them a fan of database decisions.
Totally. And yeah, totally.
Totally agree with.
And I think with that, probably we have few more questions, but probably we'll write a blog article around it. But pretty much we covered most of the questions. And thanks a lot, Tom, Tina, and Louis. It was great interacting with you, and the session was really insightful. I could revise a lot of concepts myself after a really long time. Thanks a ton for that. And I can see that the audience have really enjoyed it thoroughly throughout.
I've been trying to keep up with the comments, and guys, thank you. It's an honor to be here. We love you all. Please, yes, thank you, Louis. Please connect with us on LinkedIn. We really want to answer you. If we don't answer you, it's not because we're ignoring you. We just somehow failed to do so. But just ping us again if we don't answer you, and consider us your new friends, please. Please.
Yeah. And thanks a lot to the amazing audience for joining in, and we will be looking forward to having more such sessions, Tom, Louis, and Tina, and let's see how we can collaborate and create an impact in the community, and looking forward for such great initiatives. Thanks a ton.
Excellent.
Yeah.
Thank you.
And, probably I'll let the broadcast be for a few seconds so that
Okay.
Yeah.
Good. I want to stay on just a little bit longer in the backstage with you, Chenyukya.
Yeah, sure.
Am I saying your name right? I'm trying. Chenyukya?
Yeah, and yeah. Also, Tom, do you want to share some final, any thoughts that you would want to share with the budding data scientists or data science enthusiasts who would want to get into the field? What is the suggestion that you would give?
An elevator speech. This is tough because we're writing a whole post on this. I'm doing a whole post on this with Manpreet and Abdul.
Okay.
So by the way, Tina and Louis are my partners in Integrated, and so are Manpreet and Abdul. But here it is, as briefly as I can say it: be a data scientist. Because you are a data scientist, do data science. Then you will have the recognition of being a data scientist. And here's what we mean by that. Guys, we know it's challenging to get a job in data science right now. Please don't worry about that. Get a job at a company you love and agree with, and then start applying the benefits of data to their work after you've finished your primary role each day. But to do don't try to presume you have enough business acumen to do that. Get to know the business people, the business leaders, find out what their needs are, start getting access to the data and showing them what the data can tell them. Care. When we summarize this whole thing, it's just learn to care. And the reason I know this is because I sucked so bad at it when I was y'all's age. Please just learn to care about your business and show them how data can help.
Yeah, totally aligned on that. And yeah, and also maybe Louis, Tina, you would want to add something from your own personal experiences.
Yes. Can I go first, Louis?
Yeah, please go ahead.
Yes. So currently I'm doing my master's degree in data science, and I wouldn't call myself an expert in this. I was a bit overwhelmed when the poster showed a discussion with the experts. So currently I'm still doing my master's in data science. So even with all this, the one thing that helped me a lot, that helped me grow in this data science field, was connecting and networking with the community and trying my small part in order to give towards the greater DS community. So that helped me, like engaging with content, engaging with or trying to connect with the big influencers in the data science field, like Tom himself. This all helped me because I used to do posts every day, and Tom used to see that, and that is why he asked me whether I would love to write. I would be okay if, to write in his blog. So I wonderfully I was very honored since he asked that, and
Our blog now.
yes, yes, our blog post. And I was very honored that he asked that. And since then, I've been trying like my part in order to contribute a part to the community and a part of my knowledge to the community. And that really helped me grow in this field. So to all the budding data scientists or aspiring data scientists, I just have to say, try connecting with the data community via LinkedIn, and it will help you grow a lot.
Totally.
Exactly.
Yeah.
Exactly. Yeah, so from me, actually I have talked about this not so while ago, like what is the recipes to boost your data science journey. So actually there are four main recipes from me. The first one is to continuously learning and gaining your skills. Like you can build your side projects, or you can continuously learning from like reading papers, like write articles or reading articles, and many more. And you can also gain your experience, like you can do the voluntary work, or even like just Tom said, you can join a company and you show them like how data can make them profitable. And then the third part is like join the community, just like the Tina said. Community is so powerful. We can gain a lot of benefit from the community, and also we can give back our knowledge to the community itself. And the last thing is you yourself. Like you have to start now. Like the most important thing is you. So you have to have a grit, and you have to start now to jump into this field. Yeah, that's from me.
Yeah. Totally. Thanks.
I,
Thanks,
I
Etan.
gotta, I want to brag on Louis real quick.
Yeah.
If any of you've read our mentorship blog post, I love all the authors that have joined me with Integrated. But when I met Louis, I said, "You're Tom. You're this fictional great mentee that's becoming a great data scientist the right way." And he was already doing all the right things. And I said, "Please join us." And so we were all ecstatic when he joined the Integrated MLAI team.
Nice. Very
But
interesting.
and I missed out the most important point. You want to check out Louis's webpage because it's a perfect example of the kind of things you can do to showcase yourself to the world.
Yeah. Totally. Probably, like, we will when we are sending out a final thank you email, we will definitely include all the profiles and other material, and also the link to the presentation as well. So we'll definitely do that. Thanks, Etan, for everything.
Thanks, Santush. We agree.
Yeah.
Yes, thank you.
Yeah. Take care and have fun. Yeah. Bye.
Yes, thank you so much.
Bye bye.
Bye.